Okay. So hello everybody. My name is Aina Andriambolamalala. I'm a student at IRIF in Paris, and I'll present a common work with my PhD advisor, Professor Vlady Ravelomanana. Today I talk about how to elect on wireless network by transmitting only one. Okay, I'll start with a brief definition with the main subject of the talk, followed by some existing results, and I'll expose our results. Finally, I'll conclude with some perspectives. So, with the distributed systems, uh, distributed system is a set of processors, computers, or maybe cells that aim to do common tasks without control. Some research shows, for example, that fruit flies cells interact distributively with each other by exchanging proteins or doing the same task as the computation of a maximal independent set. As you can see here, in addition to maximal independent set, there are much more distributed computing tasks as the consensus task, which is the basis of uh, the blockchain algorithms, the leader election, which is of interest in this talk. Many aspects of these problems as the time complexity, the message and complexity, or the energy complexity. So there are also many communication models in the distributed area, but we are interested in the radio network and the BP network model. In radio network, time is subdivided into discrete synchronous slots. At any time slot, a node can transmit a message, listen to the network, or remain idle or asleep. A transmitting node can't hear that any of its neighbors transmit or not, depending on the collision detection capability of the devices. Only the listening nodes can know if one or none of its neighbors transmit. We are also interested in the BP model. What differentiates this model from the radio network model is that a node can only transmit a beep or a single bit message. On this talk, we also focus on the single hop network for which all devices are in the communication range of each other. On this later model, we are interested in the leader election problem, where all the nodes aim to agree on one node to be the central controller by exchanging messages. Most of the time, the components of a distributed system are battery powered. So the communication on the network costs more energy than internal computation, and the energy complexity of the algorithms is measured by the maximal number of time slots during which some node sends a message or listens to the network. So I'll show some existing results. A basic ID for computing a leader election, supposing that all nodes know their exact number n, is for all nodes to attempt to be the leader with a probability of 1/n. This intuitive ID presents some constraints. Instead, uh, it has has a lower bound of time complexity of omega of log n to succeed with high probability, and it needs the nodes to have the ability to hear if it transmits alone or not. This ability is called the strong collision detection ability. Some other results have been presented for this radio network with strong collision detection model. When n is unknown by the nodes, there is an algorithm electing a leader in O of log to the epsilon n expected time slot and having O of log n energy complexity. In the RNCD model, an algorithm has O of n time complexity with high probability and with O of log star n energy complexity. We note that finding an upper bound of n takes O of log star n energy complexity. So, what are our results? For the RNCD model, we designed an algorithm with almost optimal O of log n and O of log squared n time complexities, and with an energy complexity of at most 3. So it has constant energy complexity when n is known by the nodes and when an upper bound of n is known by the nodes. Our main idea is inspired by the ball and pins problem. If each of the n nodes generates one random value, and if the maximal of the generated values is unique, the node holding this maximum value can be found by a dichotomy in O of log n rounds and gets elected. With this basic idea, we found a suitable probability distribution. Here, the geometric distribution with half parameter, for which, if we sample n random values, the value log n minus 1 and the value log n are respectively held by unique node with a constant probability. So, having these properties, when the nodes know n, our algorithm works as follows. Each node firstly generates one random value using the geometric distribution. Then the node having the value log n minus 1 transmits a 1-bit message. If the other nodes receive a message, the node having log n transmits a 1-bit message. And finally, if the first node having log n minus 1 receives a message, it becomes the leader and all the other nodes become eliminated. By the previously present property of the geometric distribution, this algorithm elects a leader with a constant probability and in a constant number of time slots. So to reach the high probability of success of the algorithm, we have to execute this later algorithm O of log n times. To do so, and to have each node transmitting only once, we do as follows. We distribute the n nodes into O of log n groups. So each group has theta of n log n nodes, and these nodes will execute the previously described constant time leader election protocol. For each group, each node in the group generates a random value using the geometric distribution. Each node verifies if it has each value in this interval I, and becomes candidate, and the other nodes become eliminated. So there are at most O of log n candidate nodes in each group and O of n log n eliminated nodes. The eliminated nodes are then distributed to witness for an election at each time slot of the algorithm, and at least theta of n log n nodes witness for an election at each such time slot. After that, after all candidate nodes in the group browse through the interval I with the following red window. The candidate nodes with the value I0 transmits a 1-bit message, while those with the value I1 listen to the network. If the listening nodes receive a message, they transmit a 1-bit message. And if the node with initially the value I0 receives a message, it becomes the leader. All the other nodes are eliminated. During each time slot of these executions, the eliminated nodes witnessing for leader election at the time slot listen to the network. And when a node gets elected to avoid another election during the rest of the algorithm, the nodes that witnessed at the time slot of the election are distributed to flood the remaining time slots of the whole algorithm. So at least theta of n log square nths nodes flood each remaining time slot after one election. The nodes after that, the nodes do the same computations for each value of the interval I. Then the nodes of the next group do the same computations, one group by one. Here we note that this node can be elected, but could be elected, but this is not impossible because of the nodes that floods these time slots. So when the nodes know n, this algorithm terminates in O of log n time slots, and all nodes wake up during at most 3 time slots. Each node transmits only once and listen to the network during at most 2 time slots. Now, if the nodes do not know n, but know an upper bound u of n, the nodes are distributed to participate to O of log u sessions instead of O of log n. So the interval E changes, and the size of the interval I becomes O of log n. This leads us to the following result, with an algorithm having O of log squared n time complexity and a constant energy complexity. So in this work, we designed a redirection algorithm having a constant energy consumption of 3 when the nodes know an upper bound u of n. Finding such upper bound u takes O of log star n energy complexity, and it will be interesting and challenging to design an algorithm that maintains such optimal energy complexity, but with a more efficient time complexity. So thank you for your attention. If you have any question, I'll be happy to respond to them.